Hello, everyone, and thank you all for joining us today. I'm Bob Crossan, Senior Managing Editor of Water and Waste Digest. On behalf of Water and Waste Digest and our sponsor, Emerging Compounds Treatment Technologies, or ECT2, I'd like to welcome you to today's presentation titled Mitigating the Impact of PFAS on Water Supply Using Advanced Technologies. The aim of this presentation is to provide those in attendance with an overview of PFAS treatment options, the pros and cons of each, and the process for selecting the optimum PFAS removal technology for a given application. Per and polyfluoroalkyl substances, also known as PFAS or PFAS, are a large and complex suite of anthropogenic compounds that have recently become the focus of the regulatory community, due in large part to their perceived risks of human health and the environment. Their ubiquitous presence, coupled with their complex physical and chemical properties, have led to significant challenges in their subsequent remediation and removal from the environment, including from surface and groundwaters. Today's presentation will include a look into physical and chemical properties of PFAS, a review of the current applied technologies and their respective efficacies and applications, focused discussions on the application of ion exchange technologies, a brief ion exchange application case study, and life cycle cost evaluations and comparisons for granular activated carbon, ion exchange, and membrane technologies for several example applications. So we will get started here in just a few minutes, but first a little housekeeping. You will notice on your viewer you have the ability to ask questions, and we encourage you to ask them, and we'll try to answer as many as we can by the end of the presentation based on time availability. Any questions we don't get to, we will answer offline. Finally, today our presenter is Steve Woodward, PhD and PE. Steve is the president and co-founder of ECT2, Emerging Compounds Treatment Technologies. ECT2 is an equipment company focused on developing and commercializing treatment technologies for emerging, difficult-to-treat contaminants. Steve's responsibilities include leading research and new product development, providing technical leadership on all projects, proposal development, intellectual property, and the communication with the engineering and remediation community. Steve's focus is currently on commercializing synthetic media technology for the sustainable treatment of PFAS, 1,4-dioxane, and other emerging contaminants. He received his PhD in environmental engineering from Purdue University in 1992. And with that, I'd like to turn it over to Steve.
All right, thank you, and thanks everybody for joining. There's no question that PFAS is one of the hottest environmental topics in the world today, and I get a lot of questions about the different technologies available, which ones are proven, how do I know when to use which technologies. So we figured the time was right to put together a presentation and share what we've learned about the different technologies and their applicability. So hopefully everybody's looking at slide 2 right now, which is the presentation outline. And so it's important to understand the properties of this class of compounds before you can really dig in and understand how to treat them. So we'll start with a primer on the properties, and then dig right into the technologies. What are the options out there? Which ones are proven? And then really importantly, what are the mechanisms by which they remove PFAS from water? And of course, it's important to understand the advantages and disadvantages, and all that feeds then into the selection, which is not as straightforward as you might think to select the appropriate technology for your given application. And then I'll provide an example application for each of the technologies and then wrap it up with a case study, which hopefully will pull things together for everybody. So slide 3 then is on the left, you'll see a depiction of a PFAS molecule, octane, perfluorooctane sulfonate. So it has 8 carbons in the chain. So the red numbers, 1 through 8, represent the carbons in that chain that represent the fluorinated carbon tail, if you will. And we think of these compounds as really being composed of 2 distinct parts, that hydrophobic tail and hydrophobic means water hating. And water is a polar matrix because of the way the hydrogen and hydroxide ions share electrons. So that's why things like sodium chloride, you dump salt in water and it dissolves pretty well because it dissociates into sodium chloride. But oil does not, right? And so oil is hydrophobic, just like this fluorinated carbon tail is hydrophobic. The other part of the compound has a very different property, and that's what we call the charged or the hydrophilic head. So detergents are interesting in that they have these two very distinctly different components, and that's really important, as you'll see, and hopefully as you'll understand, and how we go about removing these compounds with different technologies. If you look over on the right, that is PFBA, and the B stands for 4, right? So there are 4 carbons in that chain, and so it's a much shorter chain, and therefore has a lot less hydrophobicity. It still has that anionic or charged head, the hydrophilic head. It just has a much shorter tail, and it has a different, instead of a sulfonate group, it's got a carboxylate group. So hopefully I'm not bearing you in chemistry, but we're going to keep this high level, and I think you'll understand how this comes into play as we move forward. Not going to spend a ton of time on slide number 4, but I think it's important to understand what EPA at least considers to be effective and ineffective treatment technologies for PFAS. Up at the top, you see most conventional treatment methods, as well as biological, low-pressure membranes, oxidation, disinfection, advanced oxidation. These are not effective at removing PFAS. So what we need to focus on are the technologies that are considered effective, namely, as you'll see here in the list, anion exchange resin, which we typically just refer to as ion exchange resin, high-pressure membranes, such as nanofiltration and even more commonly reverse osmosis, and then activated carbon. And you see these removal percentages. They're rough guidelines. We have numerous systems that employ ion exchange resin that have achieved 100% removal of PFAS for extended periods of time. So, but what this does, if we go to the next slide, is really just leads us into a summary, a more simplified summary of the proven technologies for PFAS removal from water. And so GAC, of course, is granular activated carbon. Sometimes you'll see it as LGAC, which means liquid phase, because they're all, VGAC is vapor phase, and that's not what we're talking about here. So you'll see interchangeably GAC and LGAC. Reverse osmosis, often referred to as RO, is that high-pressure semi-permeable membrane. Single-use ion exchange resins, and then regenerable ion exchange resins. And as I walk through the presentation, you're going to learn a lot more about each of these technologies. And so starting off then with the mechanisms, the primary mechanism by which granular activated carbon, or GAC, removes PFAS from water is adsorption. And that really is accomplished by the tail, that hydrophobic tail that we talked about earlier on the compound. It doesn't fit well in the water matrix, so it achieves a lower state of free energy adsorbed onto activated carbon. Another way to put it is van der Waals forces take over and cause the PFAS compounds to stick, to use a general term, to stick to the carbon. Reverse osmosis is it's really a flux of water being the solute, simply referred to as size exclusion, where water passes through a very fine membrane, but the ions and the larger molecules do not, and that's a way of separating PFAS from the clean water. And then both single-use ion exchange resin and regenerable, in-place regenerable ion exchange resin, both use two mechanisms, both adsorption and ion exchange. And I will dig into the details and help clarify what that means as we move along. So let's talk about GAC for a minute. And on the left, you'll see a very rudimentary depiction of a GAC granule. Okay, and so the important thing, well, there are several important things about GAC. Number one, it's not a really fine-tuned, highly engineered product. We start with things like coconut shells or bituminous coal, and then these are pyrolyzed or charred to enhance their adsorptive properties and create a bunch of pore space so they have a lot of surface area. And if you look at those little blue things that have a little negative charge in the circle, that's that anionic or hydrophilic head, and then the little squiggly line is that hydrophobic tail, that fluorinated carbon tail. And so the primary mechanism of action when we flow water through a vessel, those are filled with these black granules of activated carbon, and as the water passes through them, the PFAS compounds adsorb, because it's really the tail that doesn't fit well in the water matrix, and it sticks on, if you will, or adsorbs on to various locations within the activated carbon. That is the mechanism of removal. Now, if we go to that block flow diagram and we consider some incoming water or influent that's contaminated with PFAS, the first step is often going to be some form of pretreatment. It could be a sand filter. It could be some sort of ion exchange resin to remove things like iron and natural organic matter as measured by TOC. But with any of these technologies, often the first step is some sort of pretreatment to remove foulants that can plug up the bed and cause high differential pressures and cause the bed to have to be cleaned. Because if you backwash the bed to remove these particles, that disturbs the mass transfer zone that's set up as we flow, typically downflow through the vessel, and that has a negative impact on the life of the carbon. So we try to remove compounds up front if necessary, and then you see lead GAC and lag GAC. Almost always use at least two vessels in series so that we can get pretty full use out of that lead vessel before taking it offline. And then when it's time, when we do get a certain amount of leakage, that vessel is taken offline and the carbon is removed, and that spent GAC is either sent to a landfill or trucked away for regeneration, and then the vessel has to be refilled with at least in the case of drinking water, almost always refilled with virgin or fresh, brand new carbon as opposed to regenerated carbon. So that's how the GAC process works. It's highly reliant on the adsorptive mechanism as defined or described on the left. Okay, so advantages and disadvantages. GAC is currently the most commonly used technology in drinking water applications, reason being that it's been around for a long time. It is not really a specific technology for removing a certain class of compounds. GAC is used to treat all different types of compounds. So removes a lot of things pretty well, but is not really targeted or specific to any specific compound. So what are the advantages? It works pretty well on PFAS, especially the long chain compounds, because remember the long chain compounds, they have that like PFAS, for example, has 8 carbons that are fully fluorinated, so there's a lot of surface area there to adsorb onto the surface of the activated carbon. So you get pretty good removal of PFAS or, say, PFOA, which is also an 8 carbon chain. Also, if you're treating a drinking water supply and it has been contaminated by sodium chloride or calcium chloride from road salt. Let's say you have a surface water or groundwater supply that's been contaminated. The GAC is not all that impacted or adversely impacted by the elevated chloride concentrations. GAC also removes a variety of co-contaminants due to its non-specificity. Those can include VOCs, chlorinated VOCs, semi-volatiles, petroleum hydrocarbons, and the like. And also, although it can't be done on site, the carbon can be removed from the vessel, put into a truck, transported away to be regenerated. Often, that transportation can be hundreds or even more miles, though, so it's certainly not a case of regeneration on site. Disadvantages, typically a much lower capacity. The GAC has much lower capacity than ion exchange resins, so you need a lot more of it. You need larger vessels, so it requires a significantly larger footprint and higher headspace. So if it's inside, it's a significantly larger building. Like I said, that carbon regen occurs off-site, so you have the vessel evacuation and transportation and then the refill. And when you do refill, it can be pretty frequent. It could be every 2 or 3 weeks, depending on the influent concentration and the size of the vessels. Moving along to reverse osmosis, if you look down in the lower left, that is a crude or rudimentary depiction of an RO membrane, where just think of it in simplistic terms as a semi-permeable membrane, a filter that has very fine pore sizes so that water molecules can pass through, but the ions and larger molecules like PFAS get rejected. And they are swept away into the reject stream. And so if we look at the process flow diagram or the block flow diagram, again, pre-treatment is very important because these membranes have very fine pore sizes, whether it's nanofiltration or RO, more typically RO. And the molecules then pass through, the water molecules pass through, but if you don't have significant pretreatment and flush away the contaminants like PFAS and iron and natural organic matter, it can lead to fouling, which is going to shorten the life of the runtime and the life of the RO membrane. So after pretreatment, interestingly here, RO membranes typically only pass about 80% of the water, so you're treating passing about 80% as clean water. The other 20% is then rejected, and then the question becomes, what do you do with that reject stream? Now, that's not a problem if you have an under-the-sink unit in your house, because you can just send that reject stream, which has the PFAS in it to drain, and that's not going to cause much of a problem. But if you have a larger scale, say, municipal drinking water plant, and you're treating 1 million gallons a day, and 200,000 gallons of that is reject, you're going to have to treat it. And so, in addition to having the RO system, you're going to have an LGAC or a resin system, and there's disposal there too. So on both ends, so that can be problematic. So in terms of advantages and disadvantages, here on slide 10, RO is currently the least commonly applied technology for treating PFAS, and is primarily used for the residential applications. It's used quite a bit for the under-the-sink treatment, but not for the larger scale, say, municipal or industrial applications. It does have advantages because it removes just about everything other than water. It removes a broad range of PFAS compounds. It is not adversely impacted by elevated chloride concentrations, and effectively removes a lot of co-contaminants. Natural organic matter measured by TOC, petroleum hydrocarbons, VOCs, SVOCs, ammonia, hardness, bacteria. So it's pretty much a catch-all for removing contaminants. On the disadvantage side, what do you do with that concentrated reject stream? If it's not an under-the-sink unit, that can be a real challenge. It also takes a lot of power to force all that water through these really tiny pores, if you will, in the semi-permeable membrane. And what you get is very clean water, but it doesn't have alkalinity or calcium, so corrosion control is required downstream, and then minerals need to be added back into the water, too, to make it safe for drinking water applications. Okay, so moving on to ion exchange resin then. If you look at the photo of what looks sort of like caviar, these are little plastic beads, plastic spheres, typically on the order of, say, 0.5 millimeter in diameter, so they're tiny. And you can picture then that you can fit a lot of these little beads into a treatment vessel. And and each one of these beads has many, many thousands of removal sites to treat and remove PFAS from water. So if you look over on the right to my simplified resin bead, it's highly simplified because there are certainly a lot more removal sites than what's shown here. But what we're trying to show is that the bead is made of plastic, and those gray lines are polymer strands, and the orange squiggly lines are cross-linking members that hold together the shape of the bead. Both of those are plastics, and so they're hydrophobic. And then the little blue spheres or blue dots those are the exchange groups, which are typically an amine group. They have a positive charge, and so we have, just like the PFAS molecules, ion exchange resins have sites that have two distinct properties. Some are hydrophobic and some are hydrophilic. So if we go to the next slide, the ion exchange resins are highly engineered. They are designed for the removal of things like PFAS compounds that have these two distinct properties. And so as a result, we get this dual mechanism of removal. Instead of just adsorption or just ion exchange, the removal is accomplished through a combination of adsorbing that fluorinated carbon tail to either the polystyrene polymer chain or whatever that plastic is. It could be a different type of plastic, typically or often polystyrene, and those divinylbenzene cross-linking members. So that's the adsorption piece. And on the other end, that negatively charged head of the compound, which is typically a sulfonate or a carboxylate, it's the ion exchange mechanism at work where the negatively charged head kicks off the chloride ion because it has a stronger affinity for that positively charged nitrogen or amine group. So I go to the next slide. We've got the PFAS compounds on the left. They're going to flow through that resin vessel that's filled with these plastic beads. The plastic beads come in the chloride cycle, so the amine groups, which are positively charged, the blue ones, initially have chloride ions attached to them. And then as the water, which is laden with PFAS, flows through the vessel with beads, we get a removal of PFAS as the PFAS compounds stick onto the resin bead at all these various sites. Now, this is very simplified. Again, each one of these beads would typically have many thousands of removal sites, but we've blown up the size of the PFAS compounds here just for simplicity to help visualize what's going on. But hopefully what you can see is that both ends of the PFAS compound are sticking to the resin bead. Unlike carbon, where it's just that purple tail, in ion exchange resin, you get both the anionic head and the non-charged or the hydrophobic tail. So what does that mean? It means the kinetics are faster, so you can use smaller vessels, less product, less media, and the capacity is much higher. So even though the vessels are smaller, the resin lasts a lot longer. The vessels last a lot longer between having to change out that resin. And so if we look at how the resin is incorporated, again, over on the right you see a photo of a typical single-use resin. Again, it looks sort of like caviar. These beads are about half a millimeter in diameter, so they're tiny, and each one has many thousands of removal sites for PFAS, or exchange sites. And if you look on the left, that's just a 3D depiction of a couple of vessels in series. And if we look at the block flow diagram, again, it's that pre-treatment up front that's important to protect the resin from fouling, to remove things like iron, manganese, natural organic matter. Then we have the lead lag vessels. They just happen to be smaller than the carbon vessels, and the resin lasts a lot longer than carbon does. And if we go to the next slide and look at advantages and disadvantages, the single-use resin, commonly used in drinking water, but also often used in groundwater remediation applications. So for advantages, because of the dual mechanism, the resins work on a broad range of PFAS, including those short chains like PFBA, PFPEA, PFBS. The footprint is much smaller than carbon, and the capacity is much higher, so the resin lasts a lot longer between replacements, which I mentioned earlier. All of these three main advantages are due to the fact that we have this dual mechanism of removal at work, and that's because the resins are much more highly engineered. We're not starting with a coconut shell. We're starting with an engineered plastic bead. On the disadvantage side, these single-use resins can't be regenerated, and then so they have to be destroyed. Typically, they're destroyed using thermal destruction, either in a cement kiln that's approved or licensed for haz waste, or it could be a haz waste incinerator, or it could be a classified haz waste landfill. The key is, though, there's a lot less of it than carbon to deal with. The short chain PFC-A removal can be impacted by high chloride concentrations, like road salt getting into water supplies. And since these resin beads are quite targeted for the mission, they don't have as wide an application at co-contaminants like VOCs and bacteria and ammonia and things like that. This slide 17 purposes to show you that because of the fast kinetics and the high capacity, the resin systems can be much smaller. If you're putting this inside a building, so let's say you're in the Northeast or somewhere where it's cold, that's going to be a much smaller building, and the headspace requirements are much less as well. Okay, now we're going to move on to the fourth of four processes, the regenerated or the regenerable resin, which our company, ECT2, pioneered in our R&D lab in Rochester, New York. And the whole idea with this is that because of the dual mechanism, these PFAS compounds stick very tightly. They bind to the resin very nicely. It's very hard to get them off, and it took a fair amount of work in our R&D lab to figure out how to make this technology sustainable. Because when you have applications like former fire training areas where the concentrations are really high because a lot of PFAS entered the groundwater, it's not cost-effective or even practical to use carbon or, in a lot of cases, single-use resin, because you're just tearing through the product too quickly. You're changing out that carbon or resin too frequently. So in those cases, you want to be able to regenerate and use the resin over and over again and do that regeneration in the vessel. So on the process flow diagram, again, it's important to have pre-treatment to remove solids, to remove iron, to remove natural organic matter. We're going to have lead lag, regenerable resin vessel. Sometimes we'll have an optional polished vessel if we're trying to achieve non-detect for all compounds. That is not typically needed. But the key here is, if you look, when that lead ion exchange resin vessel starts to leak a certain amount of PFAS, it's taken offline. The rest of the system continues to operate. And then the regenerant solution, which is a brine alcohol blend, is then pumped countercurrent through that lead vessel to clean it, to wash off the PFAS. It typically takes between 6 and 8 hours to do that. And again, the system doesn't even have to go offline. It's just that vessel's bypassed for that short period of time. And then that spent regenerant solution is recovered using a combination of distillation followed by superloading, a process that we developed, which those two processes recover the alcohol and the brine so it can be reused. And ultimately, what you end up with is a very small amount of solid waste. So basically what we're doing is we are using a series of concentration steps. Let's say we start with 1 million gallons of very contaminated, highly contaminated groundwater from a Air Force base or an airport, fire training area. That PFAS is concentrated on that lead ion exchange vessel. Then when it's regenerated, it's further concentrated into this spent regenerant solution. And then distillation, because alcohol boils off at a lower temperature than water, the vast majority of the regenerant solution is recovered that way, and then the rest, the brine, is recovered using superloading. So if you start with 1 million gallons of highly contaminated water, you end up with less than a gallon of solid waste. So as I'll show, it almost doesn't even factor into the O&M cost. It's such a small amount of waste and such a sustainable approach. If you look at the photos on the left, the top one is one of our systems in Australia, where those vessels, the doors come off, and they're either hinged or they slide, and when a vessel needs to be regenerated, a fork truck can come, take it, and carry it to the regen facility, which you see down on the lower photo. Again, it's a containerized system. You see the distillation unit inside that container. In the background is the superloader. That's where all the PFAS waste ultimately ends up. And these systems typically run for a year, sometimes 2 years, without having to take any of the resin, which is superloader resin, out of those vessels. So not uncommon to run one of these systems for a year, year and a half, 2 years without producing any PFAS waste that has to be taken off-site. So very sustainable from that perspective. Advantages and disadvantages. These regenerable resin systems are most commonly used at remediation sites where you have plumes, source zones, or hotspots where they've used a lot of firefighting foam, or it could be wastewater, or it could be landfill leachate, but high concentrations. The resins, just like single use, are effective on a broad range of PFAS compounds. The removal capacity is much higher than carbon, so you can use smaller vessels. It's almost always the lowest life cycle cost for these high concentration in the part per billion as opposed to part per trillion, or microgram per liter as opposed to nanogram per liter waste concentration, PFAS concentrations. That resin is regenerated on site. It stays inside the vessel. And then it's really a huge win if you can have, and we have multiple sites like this in Australia, where you can have, one site has 4 treatment systems, PFAS treatment systems, resin systems, that share a single regeneration system. So once you put that regen system in, you can operate multiple ion exchange systems that are treating water. It could be surface water, it could be groundwater, it could be both. On the disadvantage side, and last but not least, it's by far the lowest waste generation process of any of these. So if you're treating a high concentration, you don't want to be hauling off carbon every 2 or 3 weeks from large vessels, or resin hauling off from smaller vessels. It's better to regenerate on site and recover that regenerant solution and produce a very small amount of solid waste. On the disadvantage side, it does require power to run that distillation process. It generally doesn't remove co-contaminants like the VOCs and petroleum hydrocarbons, because these compounds, these resins are pretty targeted for PFAS removal. And then the regen system is not approved for drinking water use in the U.S., not NSF approved. So these systems are more for remediation. Okay, so how do you select a technology then? It's not as straightforward as one might think. As you can see on the left, you can't read it obviously, but this is a portion of a model that we use to plug in the inputs and select the most cost-effective technology. Those inputs include things like the influent PFAS compounds. What do you have for PFAS compounds, and what are their concentrations? Also, Are we trying to get just PFAS plus PFOA less than 70 parts per trillion? Or do we have people drinking the water and they don't want any PFAS in their water? The power cost, is it expensive power? Is it cheap power? That comes into play, especially if you're considering reverse osmosis. The co-contaminants and foulants are important, as we just discussed. If you've got high chloride concentrations, that can impact the resin's ability to remove those short-chain carboxylates like PFBA or PFPEA. Very important, the liability and associated with disposal and how you plan to get rid of that, the waste that's generated is very important, and then also the footprint that it's going to take up. All of these come into play, get figured into the model. It's not straightforward. It's certainly not one size fits all, but this is how it's done. And now I'm going to quickly go through some applications. An example of a carbon application could be where you've got a drinking water, so you're in part per trillion range concentrations. That drinking water has elevated chloride concentrations from road salt entering the wells or the surface water. You've also got some chlorinateds in there like TCE and or PCE, and you have to remove, importantly, you have to remove that at least one of the short chain carboxylates like PFBA. If you have the combination of the elevated chlorides and you need to remove a short chain carboxylate like PFBA or PFPEA, that's where carbon typically wins the day. Okay, and if we look at the next example, well, when does RO win? What's an example application where RO is the most cost effective? Well, again, it's typically going to be used for drinking water, where you're in the part per trillion level instead of the microgram per liter or ppb concentration level. The chloride concentrations, again, could be elevated or not. It doesn't really matter with RO because the only thing that's really going to pass through this membrane is water. So the TOC will also get rejected, so that won't matter. And you can have non-detect for all monitored PFAS compounds because if it's done properly, it should reject those PFAS compounds. Really importantly, though, these pumps are high pressure. They use a lot of power. You're going to want to be in an area that uses or has a low unit electricity cost. And most importantly, how do you get rid of that call it roughly 20% reject stream? Again, if it's 1 million gallons a day that you're treating, so it's a big municipal system or medium-sized municipal system, what do you do with that 200,000 gallons a day? Again, if it's an under-the-sink unit, it's not a big deal. But even if it's a whole house or a whole apartment building system, it can be a problem. The next slide focuses on an example of when single-use resin is the right application or is the most cost-effective solution. And this could be a drinking water, or it could be a remediation system. It could have a low. The important point here is that the single-use resin has a very broad application. But for this particular, I'm just providing one example. We've got 3.5 micrograms per liter or parts per billion. Chloride concentrations are normal in that, so let's say it's 45 as an example. And you're in a town, well, let's say you're in New Jersey or New Hampshire, where you've got a handful of compounds PFAS compounds that need to be removed down to really low levels. But you also have consumers that don't want any PFAS in their water. Okay, so the nice thing about that single-use resin is it can remove all these compounds, and I'm going to show you some example data to back that up. And so there are a lot of applications where single-use resin is the way to go. And then finally, on the applications, regenerable resin, like I've mentioned a couple of times here, is most applicable when you have groundwater remediation. So a good example would be you've got influent PFAS concentration in the 100 micrograms. It could be in the tens or the hundreds of ppb or micrograms per liter. Chloride could be high, it could be low. The treatment objective often in these situations in the States is PFAS plus PFOA less than 70. And it's really important to the client that they minimize their liability by reducing or absolutely minimizing the amount of waste that's transported off-site. And so you see where on the plot, the lines cross at about 7 or 8 years and after that, the regenerable resin is the most cost-effective. Prior to that, single-use. Those lines cross a lot sooner, and the economics become a lot more compelling if you either have higher PFAS concentrations or you can use central regen. Because once you pay the capital cost for the regen facility, it can serve 4, sometimes even 5 different PFAS removal systems, pump and treat systems. So just suffice it to say, if you've got PFAS concentrations in the order of, in the part per billion range, you should be looking seriously at a regenerable resin treatment system. Okay, now we're going to go through a case study and then wrap it up. This happens to be in Portsmouth, New Hampshire, and it's a remediation and drinking water application. So it's the former Pease Air Force Base in Portsmouth, New Hampshire, and the treatment system that was put in to clean up the hotspot or the source area where they did the fire training for decades is rated to treat up to 200 gallons a minute of highly contaminated groundwater in the 60 to 100 part per billion or microgram per liter PFAS range. And also on that base, there are a couple of different local drinking water supplies that are being impacted. So the main challenges here were that we had very high PFAS levels because it's the source zone. They conducted fire training for decades. It rains. That firefighting foam, which is loaded with PFAS, goes into the groundwater. Also, there's jet fuel in there, so that had already been remediated, but caused reducing conditions where iron gets liberated and natural organic matter in the form TOC was quite high. And a few years ago, a temporary GAC system was put online, but because of the high incoming PFAS concentrations, these vessels were large. The GAC was being replaced every 2 to 3 weeks, and there was a lot of waste generation, and it wasn't very economical. So the Air Force reached out to their consultant, Amec Foster Wheeler at the time, which is now Wood PLC, and said, is there a better way to do this? And Wood knew about our regenerable resin technology, and so the Air Force decided to do a side-by-side pilot test whereby they would look at having a GAC system running parallel with our regenerable resin system. And long story short, after several months of pilot operation and data collection and analysis, the regenerable resin system proved to be more effective at removing PFAS and had a lower life cycle cost. And so back in April of 2018, a full-scale regenerable resin system is actually serial number 1. There are a bunch of them around the globe now, but this was the first one in Portsmouth, New Hampshire. And it, like I said, started up in April of 2018. It's produced PFAS-free water throughout and has not created any waste that's had to be transported off-site. Over in the photo on the lower right, those on the far lower right, you see a couple of fiberglass vessels. That's the superloader resin, and that's been collecting all the PFAS. And we've treated tens of millions of gallons of water. That has not had to be changed out yet. So no PFAS waste leaving the site yet. Very sustainable process. Now, interestingly, another plume, there are multiple plumes at this base, as there often are, and another plume was contaminating the city's 3 wells, 3 of the city's drinking water wells, Smith, Harrison, and Haven wells. And so the city saw what the Air Force was doing. They said, wow, we like this resin performance. The city also had a temporary carbon system online treating their drinking water, but they got with their consultant, Weston and Sampson, and said, we'd like to also conduct a side-by-side pilot study. And in this case, we're going to look at the single-use resin that ECT2 has versus carbon, and we're going to sample for 23 PFAS compounds in and out of each of the columns and then plot breakthrough curves. And Weston and Sampson will do a life cycle cost analysis to select the most cost-effective technology. And so the next 3 slides are the output from that pilot test. And so the first one is the removal comparison of PFAS plus PFOA of carbon or GAC on the left and ion exchange resin on the right. And so in both of those plots, that dotted line at the top represents the influence PFAS plus PFOA concentration. It's the same for both, which it should be, because the pilot units were running in parallel. What is striking, though, is how quickly in the 2.5 and 5 minute empty bed contact time, and empty bed contact time, by the way, just refers to the hydraulic residence time in the vessel. So a 10-minute empty bed contact time is going to be a bigger vessel than a 2.5, can be 4 times the size if it's treating the same flow rate. And so if you look at the blue line, that was really, the 10-minute was really the only one that provided any reasonable performance, which tells you why these carbon systems are typically never designed to remove PFAS at an empty bed contact time of less than 10 minutes, because it's just not enough, there's not enough affinity. That absorptive removal mechanism is not strong enough, so you need a pretty big vessel. And so once the 10-minute breakthrough curve hit or got close to 70 PPT, PFAS plus PFOA limit, which is a health advisory level set by EPA in the States, they shut that down and said, okay, we've seen what we need to see. Meanwhile, in that parallel unit that's graphed over on the right, even the 2.5 minute, the smallest resin vessel, went for a year without any breakthrough of either PFAS or PFOA. So what does that tell you? It tells you that you can use a much smaller vessel, much smaller empty bed contact time or hydraulic residence time, and it's still going to last a whole lot longer. So definitely advantage to the single-use resin compared to carbon on PFAS and PFOA removal. Let's look at the most difficult compound to remove, which is PFBA. It's got a very short chain, only 4 carbons. It's got the carboxylate. And if you look at the carbon, even the 10-minute had very little capacity. And what's even more striking is the fact that the effluent concentration from the 5 and 10-minute carbon columns actually had a higher PFAS concentration or PFBA concentration than the influent for a period of time. And that's called chromatographic displacement, where you get this temporary removal of PFBA, and then the longer chains like PFAS and PFOA or PFHPA, PFHPS come along and knock the shorter chains off, and for a period of time you can get even higher than the influent concentration. If you look at the ion exchange resin on the right, it had decent PFBA removal. These are more classic breakthrough curves, where you had the 2.5 broke through the smallest vessel first, as you'd expect, followed by the 5-minute, followed by the 10-minute. If we look at, so again, advantage resin, one other example, PFBS. So again, the carbon did not work all that well on the PFBS, certainly better than it did on the PFBA, which tells you there's something more than just absorption going on here. But look at the resin. The sulfonate group has a much higher affinity for that amine group on the resin because of electron density. And so even that 2.5 minute, even with that short chain, that 2.5 minute, the smallest column, performed very well and had no breakthrough of that short chain PFBS, even in a year's worth of operating data. Just shows the power of that ion exchange mechanism when you think about the dual mechanisms of removal. And so getting to the end here, my last slide is the summary, and hopefully what you've walked away with is the fact that there are really 4 proven PFAS removal technologies on the market. 3 are really proven at full scale so far. There is ongoing work to prove out RO at full scale, but the vast majority, really vast majority of those systems are under the sink units in people's homes that treat very small amounts of water. So the ones that are proven at a reasonable full scale are GAC, single-use ion exchange resin, and regenerable ion exchange resin. But the real take-home message here is that it's not a simple process or exercise to pick the right technology for your application. There are a lot of factors that go into it. There's due diligence, there's modeling, there's a lot of homework, that should be done to ultimately pick the most effective and the most cost-effective technology. And so with that, we have about 8 minutes for questions, and I'll hand it back to the moderator to have a little Q&A session. But I thank you very much for your attention and your attendance.
Yeah, thanks a bunch, Steve. This is a ton of information, really helpful. So yeah, we'll just start right in on some questions here. We have quite a few to get through, we'll try and get through as many as we can. The first one here, have you done a life cycle cost analysis comparing the different technologies on different waters? If so, can you share results? Which technology has the lowest life cycle cost, and what are the reasons it has the lowest cost?
Yeah, I think that question was probably submitted before we got to the comparisons, because I think that's really we covered most of that in the presentation. And which one has the lowest life cycle cost depends on a number of factors. And I think just to summarize it quickly, if you think about carbon, it's going to have the lowest life cycle cost when you have a couple of factors. You've got high inorganic anions, particularly chloride, often from road salt, and you have to remove that short chain carboxylate PFBA or maybe even PEA or PFHXA. The single-use resin has very broad application, but does not work well if you've got high chlorides and need to remove those short chain carboxylates. And then the regenerable resin is going to be the most cost effective when you have high concentration. Let's just say you get to 10 or higher micrograms per liter or ppb on your total PFAS. That's when you should be taking a hard look at regenerable resin, especially if you have the opportunity to use the central regen concept.
Got it. Cool. Next one here. Are you seeking NSF 61 approval in the U.S. to use regenerable ion exchange resin technology in drinking water?
We definitely are looking into that. We actually do have a drinking water system overseas that uses the regenerable resin technology. It's really a question of the alcohol that's used in the regen system and demonstrating that alcohol is flushed out prior to the system being put back online. So that is underway, yes.
Awesome. And here's another one. What are the health risks if you are running a GAC system?
The health risks are not very severe. One thing that can happen when the GAC system is started up is that you'll get a temporal or a short-term pH shift out of a range that would be considered normal or healthy. So that some pH adjustment often needs to be taken into consideration. There have been some other minor compounds that have formed on the carbon and then elutriated off, but those have been real isolated incidents. So I'd say it's mainly the pH phenomena. Sometimes there are metals that, if the resin is not acid washed, there could be heavy metals that come out when the system's first started up. Those are the main things to look out for. Okay.
And then, why hazardous waste disposal for single-use ion exchange?
Well, fortunately, the resin has a high capacity, and we don't use a lot of it. But the question then becomes, what do you do with it? You could put it in a landfill, and it doesn't have to be a hazardous classified landfill. It's not illegal to do that, because other than New York State, it's not considered a hazardous waste. But the challenge is future liability, right? What happens when classifications change, and if you do get some leaching of those PFAS compounds back off the resin, you definitely want to have them in either a lined landfill or have them destroyed through thermal destruction. Just like in carbon systems, when they go to regenerate, that the idea is, and I'm not sure that it's been proven anywhere that these thermal processes are 100% effective at destroying PFAS. But so it could be that aligned classified landfill is going to be the best bet.
Got it. Okay. And then here's another one here. Could you theoretically use your ion exchange resin regeneration technology, distillation and superloading, for instance, and combine it with an RO treatment process to concentrate and treat the supernatant waste?
You definitely could do that. And in fact, we have explored that in the lab. It's really a question of cost effectiveness, right? If you take the waste product that's left after the distillation and recovery of the alcohol, and then the superloading and the recovery of the salts, or let's just say after distillation, you're going to have a very high brine concentration. It takes a lot of power to then force that through the membrane. It's not a lot of volume, though. So one of the things we've looked at is, well, instead of using the distillation and superloading, to just use membrane technology. And we haven't had a ton of luck yet with a limited amount of testing, but we do continue to work on that. I think it might be a feasible process. And I think it's also maybe possible to use the two in a different way, where RO could be used as the primary treatment mechanism, and then that 20% reject stream could then be used. Let's say you have in the vicinity, you have a regenerable resin system where you can cost effectively take that reject stream and treat it and produce a low amount of waste. There are ways that these technologies can work together. So it's a good question.
Awesome. Cool. Yeah. Here's another one that we have, and it is, does GAC absorption for PFCs change with TOC?
It does, absolutely does. TOC in these waters is very commonly caused by natural organic matter. Natural organic matter are these large, chunky organic compounds with lots of benzene rings and other cyclic features, and they can really foul up activated carbon and take up capacity and reduce the carbon's capacity to remove PFAS compounds. So very important to look at a natural organic matter, which is typically measured using the TOC test.
Cool. And I think that we have time for just one more here. Could you speak to initial capital costs of ion exchange versus GAC? How do they differ? Which one's greater? Which one's less? So on and so forth.
Good question. I think I inadvertently skipped a slide. I did. So hopefully everybody can still see the slide. It's slide number 33. This was the output from the pilot test in Portsmouth on the drinking water. And in this case, now, resin does have a higher unit cost. So cost per cubic foot or cost per pound is higher for resin than it is for carbon. But if you look at the capital cost comparison that came out of that side-by-side pilot test, which ran for over a year, the resin capital cost is lower than carbon, and that's because the vessels are 1/3 the size, have a much lower headspace requirement, so the building is a lot smaller. So you're using less resin, even though it's more costly on a unit basis, and you have a smaller building. So the capital cost is lower. The operating costs are much lower because, again, you're replacing a lot less material, a lot less frequently. And in this case, the independent consultant, Weston & Sampson, found that overall, with a 20-year present worth analysis, the resin system was 57% less expensive, so well less than half the cost of the carbon system on a life cycle cost basis. So I think in some cases, not all cases are the same, and that's why you should run the calcs and do the modeling. In some cases, the carbon could have an equal or even slightly lower cost than resin because of that unit cost differential, but the operating costs are typically lower, And so it's the life cycle cost that typically wins the day on these projects, because you're usually not cleaning up PFAS for a year or two. Usually that treatment or remediation goes on for decades.
Awesome. Well, thank you so much, Steve, for all this information. That wraps up our questions in this webinar. I know we had a lot more questions in the queue here, but we didn't get to them. But any of the questions that we didn't answer, we will answer offline. On behalf of Water and Waste Digest and our sponsor, Emerging Compounds Treatment Technologies, or ECT2, I would like to thank everyone for your participation. This webinar will soon be archived at the same URL you used to visit the webinar today, and it will also be present on www.wwdmag.com and can be viewed on demand, so feel free to share this with others. Thank you so much for attending, and so long, everyone.
Thank you.